Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is coin change. First of all, let us start by understanding the question. So what does question say? It says that given an integer array coins of size n representing different denominations of currency and an integer sum, find the number of ways you can make sum by using different combinations from coins. Okay, so what it's basically saying is that in the input we are given an array named coins which is of size n, and we are given an integer sum. Okay, now we need to tell how many different combinations of this coins array is possible, such that the sum of that combination, the sum of the coins which are taken in that combination, sums up to sum. Okay, let's read further. It says that assume that you have an infinite supply of each type of coin and you can use any coin as many times as you want. So here there are n different types of coins. Each coin we have infinite supply. So ith coin we have infinite supply of this coin. Okay, so we can take the ith coin multiple times, one time, two time, three time, as many times as we want. Okay, all the coins, for all the coins we have infinite supply of them. So basically we need to tell the number of ways of picking up coins from this array such that each coin can be taken multiple times because it has an infinite supply, and the set of coins which we select sums up to sum which is given in the input. We have to tell the number of ways to do this. Okay, now let's go further. So if we look at the example here, there are three different coins, 1, 2 and 3, and the required sum is 4. The output is 4 because there are 4 different ways of doing this, that is 1 1 1 1, 1 1 2, 2 2 and 1 3. Note here we are only asked the number of ways in a particular way. We do not need to consider different arrangements. For example, 1 1 2, 1 2 1, these are all same only. We need to tell just different number of ways. Okay, then the second input is n is equal to 4 with the required sum is 10. These are the coins and there are 5 possible ways. It says that you do not need to read input or print anything. The task is to complete this function which accepts array coins and its size and sum as input parameters, and return the number of ways to make change for the given sum of money. So basically it says that the sum integer which we have, can we make a change of that much amount using our coins, then in how many different ways, that we need to tell. The expected time complexity is sum star n, and the expected auxiliary space is big O of sum, and here are the constraints. Now see, what we can do is, first of all, it is said that we have an array of coins and we need to find out number of ways of selecting coins such that their sums up to sum which is given in the input. Also each coin can be taken infinite number of times. Now what we can do here is, the brute force approach can be the recursive way. We can for each coin select either to pick it or not to pick it, and whenever we reach sum equals to 0, we will say that it is a one way to do it. For example, so if we try to draw the recursion tree for the given example, that we have the coins 1, 2 and 3 and the sum is required is 4. Now let's start from the last index. So I am talking about the coin which has value 3. Either I'll take it or I'll not take it. So suppose I take it. If I take it, then the required sum would become 1, because initially it was 4. I took one coin having denomination currency value 3. So the required sum becomes 1, and the set from which I can pick up the coins still remains 1, 2 and 3. Until I want, I'll keep picking a single coin. As soon as I select not to pick it, further I will not pick it. But I can pick it any number of times because we have infinite supply of each of the coin. Or so either I pick it or I don't pick it. If I don't pick it, in the next step I have the set 1, 2 and the remaining sum is 4. Now again for this, either I pick the value 3. So if I pick the value 3, I can also pick it in next step and the remaining sum becomes -2. Or I do not pick it. So if I do not pick it, then the remaining set is 1 2 and the sum remains 1 only. Similarly here I decide to pick 2, so if I select 2, in the next step also I can select and the remaining sum is 2, or I decide not to pick it. Okay, so if I decide not to pick it, the remaining sum is 4 only, and now the set available is only 1 coin. Now here, since the sum is negative, it means we will never reach sum 0. Sum should reach 0. When we reach 0, it means we have got the required sum. So here I'll return 0, that this way is not possible. Okay, now suppose I use 2, then what will happen? The sum required will become -1. Or I do not use 2, then the next step I have only 1 coin and the required sum remains 1. Suppose I use 2 here, then in the next step also I can use 1 and 2 and the required sum becomes how much? 0, because I have used a coin of 2, so the total remaining sum becomes 0. Or if I do not use it, then only 1 will be left and the required sum left will be 2, and so on. I can fill for this. Now suppose I take here 1, okay, then in the next step also I can take it, and now the required sum is 0. Whenever we reach required sum equals to 0, it means we have taken the coins such that their sum was equal to sum. Go back to this path. See, first I didn't took 3, then I decided, sorry, here I took 3, so the sum became 1. Then I decided not to take 3, then I decided to not to take 2, and then I decided to take 1. So I took 3 in the first step and 1 in this step, so overall 3 plus 1 became 4. Okay, so in this path I got one combination, so I'll return 1. There is one way. Okay, similarly, anywhere I get some negative, it means this is not possible, we will return 0. Also, whenever the sum remaining is positive but the set becomes empty, then also we need to return 0. For example, in this case, suppose I decide not to take this also, then what will happen? This set will become empty and the required sum is still 2. Now it is not possible because the set is empty, so I'll return 0. So basically what we did is we recursively called the coins which we can further take and the required sum. For the last coin, we decide whether to take it in this step, whether to consider it, or whether to not. Also, we had infinite supply of each coins, so when we decide not to take it, we will not take it further. But when we decide to take it, so for example we decided to take 3 here, then we will not remove it from the set of coins which we can take further, because we have infinite supply, so we will keep taking it until we want. But as soon as we say okay, now we do not want this coin, then we will remove it from the set. So this will be the recursive approach. Here, whenever the sum becomes negative, will return 0. Whenever sum becomes 0, will return one way, and whenever the set becomes empty but the sum is still positive, we will return 0, because now we cannot do it. So if I write this function, first of all it will have the size of the remaining set n and the required sum. If sum equals to 0, then return 1. If the sum is negative, it means now we cannot get the required sum, so return 0. If now sum equal to 0 and sum less than 0, two cases are over, so now sum will be positive only for remaining cases. But if n equals to 0, return 0. What does this mean? It means that sum remaining is still positive but the set has become empty. So, and the last case can be the sum remaining is also positive and the set is also not empty. So what we will do? We will call two recursions, in which we will take in one recursion we will consider the last coin, and in one we will not. So for example, here the set is not empty and the sum is also positive, so here we considered the last coin, here we did not consider. So then what we will return? We will return function. Suppose we consider the last element, then the total number of remaining elements will be n only, and sum will become sum minus coins of n minus 1, because I am considering the nth coin. It will be at index n minus 1, so the remaining sum would be sum minus this, and the remaining set will have still n coins, plus function. Now I do not want to consider this, so this becomes n minus 1, and if I am not considering it, the sum will remain as it is. So we will return sum of these two recursions. Like for this, we called this recursion as well as this recursion, and then their sum will be sent. Okay, so this is the recursive function which we solve. Now in this recursion function, it will take exponential time, right? It will search out for all the possibilities and it will give time limit exceeded. So we need to think of converting it into polynomial time. The expected time complexity is a sum star n, right? Second thing, if we can, now we need to convert exponential into polynomial. If we can see that overlapping subproblems property and optimal substructure property is satisfied, then we can say that this problem we will be able to solve using dynamic programming. So can we see those properties? See, what is overlapping subproblems? It is nothing but the same subproblem is solved multiple times to reach to solve the bigger problem. So now if we look at here, see here in the set we have one currency with value 1, and the sum required is also 1. Now suppose here I consider 1, then what will happen in the next step? The set will have 1 and the required sum will become 1 because I considered it. So 2 minus 1, 1. So can we see the repetition of subproblems? So there is overlapping subproblems property. Does it also have optimal substructure property? It means that we are using the solutions to the subproblem and using it to solve the bigger problem. Here to solve the function n comma sum, we are using the smaller problems having one less coin, or either the sum value becomes less. So we are using the solution to the smaller problem, and using them we are defining the bigger problems. So we also have optimal substructure property. So this problem can be solved using dynamic programming. Now let's see how we can solve it using DP. So now if we discuss the dynamic programming approach, then first of all let us decide what kind of, so we will follow the tabulation method here. Now what would be the table structure? See, we here have two things. First, the number of coins, and second is the sum required, right? So here in the recursion, as we solved, what we did, we were passing two things, that for this set of n numbers and the required sum, what is the number of ways of doing it, right? And here we are saying the in here the set remains same but the sum decreases. Here the set decreases, sum remains the same. So what we can do is we can take dp of n plus 1 and sum plus 1 size. Okay, here dp of ij will denote the number of ways. Remember here carefully, the number of ways to reach sum j using the first I coins. The number of ways to reach the sum j using the first I coins, that is what this will denote. So at the end what we will return? We will return dp of n sum. What this will denote? Number of ways to reach sum using the first n coins, that is basically using the whole set which is given, right? Now first of all we need to define the base cases for this table. So initially I'll mark all the elements in this 2D matrix as 0. Okay, now understand one thing, in the recursion call when we were getting sum 0, we were saying it is a valid thing, right? Either we had elements in the set or even if we didn't. Why? Because you can reach sum 0 in one way, either you have 2 elements, 3 elements, 4 elements, or any number of elements, by not selecting any of them. Suppose you have elements 1, 2 and I ask you how many ways to reach sum 0. Only one way. How? Do not select any coins, right? So for I can say for I equals to 1 to n, dp of I comma 0 is equals to 1, or even I can say here 0, because even if you do not have any coins, you can make some 0 by not taking any coins, right? So dp of I0 is equals to 1. Now for I equals to 1, I is less than equal to n, I plus plus, right? The coins for loop I am keeping it outside. Why? Because for a particular coin we will take all its possibility, right? We will take it as many times as we want, then we'll move on to the next coin. So for I equals to 1, I is less than equal to n, I plus plus. For j equals to 1, j is less than or equal to some j plus plus. Okay, now here basically I am finding the number of ways using the first I coins to reach the sum j. Okay, now either I'll be considering the ith coin or I will not be considering it. See, when I am considering ith coin, its value should be less than equal to sum. Suppose the required sum is 4 and the ith coin value is 6, then there is no point in taking it, right? So we will put a condition here to check that, because we do not want this indexes to go negative, because I and j basically will be replaced here, right? So only if the value of the ith coin, that is coins of I minus 1, because the ith coin will be at I minus 1 index, is less than or equal to j, then dp of ij is nothing but dp of I j minus coins of I minus 1. What does it say? Suppose I considered the ith coin, I minus 1th coin, so the remaining sum would be j minus coins of I minus 1, and I need to count the number of ways to reach this sum up till coin I, plus dp of, here I considered I minus 1th coin, I minus 1 indexed coin, now I do not want to consider, so dp of I minus 1 and j. See, look at this formula again. Number of ways to reach sum j using the first I coins is number of ways to reach the sum j using first I minus 1 coins, plus number of ways to reach the sum j minus coins of I minus 1, because I considered the ith coin using the first I coin. So this is when you do not consider the ith coin, and this is when you consider the ith coin. Else, if the value of that coin is greater than j, if the j, that is the required sum, is 6 and the coin value is 8, you cannot consider it even once. So in that case, dp of ij becomes dp of I minus 1 j. Number of ways to get sum j, I'm sorry for the handwriting, number of ways to reach sum j using the first I coins is number of ways to reach sum j using first I minus 1 coins, because ith coin we cannot consider anyways, right? And at the end what we will do is we will return dp of n and sum, which will be our required answer, right? What will be the time complexity in this case? It will be big O of n into sum, because we are running a loop of size n, and inside that we are running a loop of size sum, so n into sum. What would be the auxiliary space? The auxiliary space will also be big O of n into sum, because I have taken a 2D array of size n cross sum. Now in the question it is said that auxiliary space is big O of sum, so you can do space optimization on this and solve it. How? You can consider an array dp1 of sum plus 1, in which dp1 of I will finally denote, after we will fill this table, it will finally denote the number of ways to reach sum I, okay, using all the n coins basically. So how we can do this? In this also we can run a for loop for I equals to 0, I is less than n, I plus plus. This is for the coins. For the sum j equals to 1, j is less than or equals to sum j plus plus. if the value of the ith coin, that is if coins of I is less than or equal to j, only then we will consider it. Also here, since I am taking I and j both in the 2D index, that's why I am taking j equals to I equals to 1 to n. Okay, here I am not taking I in any index, so I used it from 0 to n minus 1 only. If coins of I is less than equal to j, then dp1 of j plus is equals to dp1 of j minus coins of I. So what it basically does is, if I'll tell you with the help of example, it will be very clear. Suppose you have a set of coins 2, 1, okay, and you need to find the number of ways to reach sum 4. Okay, how many ways could be there? 3 ways: 1 1 1 1, 2 2, and 1 1 2. There would be 3 ways. Now in the dp1 array, you have 0 index, 1 index, 2 index, 3 index, and 4 index. Okay, also dp1 of 0 is equals to 1, because there is only one way to reach sum 0, that is not take any elements. Now, so this is 1, these all are 0. Now when I am looping by, see, outer for loop is for coins, so when I am looping outside, first the coin value is 2. So can I take it here? No, because coins of I, the value of that coin should be less than equal to j. This is the value of j, so I cannot take it here. Can I take it here? Yes. dp1 of 2 will be plus equals to dp1 of 2 minus coins of 2, sorry, coins of 0. Coins of 0 is nothing but 2 in the first for loop, so this will become 0. So basically this will become how much? This will become 1. Again here also I can do that, so dp1 of 3 will be equal to dp1 of 3 plus dp1 of 1 using this coin. This is also 0, 0 plus 0, this will remain 0 only. And it is true, because using only coin 2 you cannot reach sum 3. Then dp1 of 4, here it will become dp1 of 4 plus is equals to dp1 of 4 minus 2, that is 2. So for here it is 1, so this will also become 1. And that is also true, using coin 2 you can reach 4 only one way, 2 2, you have to take 2 coins of 2. Now the outer for loop increases and we come to coin number 1. Here it will become dp1 of 1 plus is equals to dp1 of 0, because j is 1 and coins of I value is also 1, so this will also become 1. And it is true, you can use one coin of 1 to reach sum 1. Here it will become dp1 of 2 plus is equals to dp1 of 1, because 2 minus 1 is 1, so this would be added here, so this will become 2. It is true, for 2 you can reach it in 2 ways, either by 2 or by 1 1. For 3 it will be this plus 2, because j is 3 and coins of I is 1, so this will also become 2, because this value will be added into it. So there are 2 ways to reach 3, 1 2 and 1 1 1. Now for 4 it would be dp1 of 4 plus is equals to dp1 of 3. dp1 of 3 is 2, it will be added in this, so I'll get 3. And there are 3 ways which we discussed initially. So this is the second method. Here we will finally return dp1 of sum, which will denote nothing but the number of ways to reach the value sum. Here the time complexity would again be how much? N cross sum, because we are running 2 for loops, but the auxiliary space will be big O of sum in this case, because we are taking only one array of size sum plus 1. Now let's see the actual code and submit it. So now if we look at the actual code, so I have taken here dp of size sum plus 1 and n plus 1. Here I have initialized all of them to 0. This is the base case. When the sum is 0, number of ways to reach it is 1 in any case, okay, no matter how many coins we are considering. Then here I have taken, if the coins of j of I is less than equal to I, in that case we can consider taking that coin. So dp of ij would be equal to dp of I minus coins of j minus 1. The sum would decrease, and we can consider this multiple times, so this will remain j only, plus If we do not consider it, so the sum will remain I only, and this will become j minus 1. Else, if the coin value is greater than the required sum, then number of ways to reach that sum is equals to number of ways to reach that sum not considering that coin, right? So dp of ij equal to dp of ij minus 1, and I'll return dp of sum n. Now this is the space optimized way, where I have taken dp1 of sum plus 1, initialize the base value as 1 and others as 0. Then using the two for loops, if the coins of I value is less than equal to j, then dp1 of j plus is equals to dp1 of j minus coins of I am considering that coin, and finally I will return dp1 of sum. Any of the ways you can do it, I am at present passing in this code. Okay, let's submit the code. Okay, so we have solved the problem successfully, and the time complexity and the auxiliary space we have discussed it previously. I hope you have understood this question completely. Thank you.